Welcome, curious minds, to another deep dive. Have you ever paused to wonder how machines learn to do truly complex tasks? Not just by, rigidly following a set of explicit instructions, but by actually figuring things out on their own. A bit like how we learn from our own daily experiences. Today, we're embarking on a fascinating journey, peeling back the layers of time to the very dawn of artificial intelligence. A period long before buzzwords like deep learning or, AlphaGo, or even a twinkle in a researcher's eye.
Indeed. And our mission today really is to unpack those foundational ideas, the ones that allowed early neural models to learn through, well, a rudimentary yet incredibly powerful form of trial and error. This is what we now recognize as the nascent, the really exciting stages of reinforcement learning. We'll explore how these visionary researchers first began combining simple, often biologically inspired neural networks with what they call reinforcement signals, essentially rewards for correct actions and clear punishments for mistakes. And you'll hear about the ingenious solutions they devised because they immediately ran into complexities, right? Things that threatened to derail these fields almost before they started.
And trust me, those initial struggles were significant. But they weren't failures. Not really. They were more like the crucible where those aha moments were forged. Leading to breakthroughs that, step by painstaking step, truly planted the seeds for some of the most impressive AI achievements we marvel at today. We're talking everything from machines mastering notoriously difficult board games to the intricate movements of advanced robotics. It's a compelling story. Scientific perseverance, fundamental insights, and this gradual, profound understanding of how machines can be taught to learn from experience. So settle in, because we're diving deep into the history of how machines learn to learn.
The dawn of neural networks. From biological inspiration to logical machines, 1940s, 1960s.
Okay, let's rewind. All the way back to the 1940s. A decade that, in so many ways, laid the intellectual groundwork for our modern thinking machines. This was a time before anyone had truly conceived of complex algorithms or vast data sets. Back then, the groundbreaking idea wasn't really about programming intelligence, but about abstracting it. The big question was, could the fundamental building blocks of something as intricate as a biological nerve cell be distilled down into a simple logical operation? It's truly remarkable how far back this biological inspiration goes.
It really is. And what's truly fascinating here is how two brilliant minds, the neurophysiologist Warren McCulloch and the logician Walter Pitts, published their seminal 1943 manifesto, a logical calculus of the ideas immanent in nervous activity. This wasn't just another academic paper, it was like a conceptual earthquake. They introduced the first sophisticated discussion of what they termed neurological networks. They weren't just tossing around abstract philosophical ideas, they were actively bridging cutting-edge neuroscience with the rigorous principles of formal logic. Their core proposition was revolutionary for the time. These networks could be built by interconnecting incredibly simple abstractions, each one based on the observed all-or-nothing behavior of biological nerve cells.
So they were essentially creating a mathematical model of a single neuron, like how it decides to fire or not fire.
Precisely. They combined these new ideas about finite-state machines, which, if you think about it, are kind of like a simple traffic light. It can be red, then green, then yellow, but never all at once, right? And it transitions based on specific triggers. They fused this with linear threshold decision elements. These are mathematical functions, basically modeling how a real neuron fires only if the incoming signals, summed up, exceed a certain threshold. And finally, they integrated logical representations for various forms of behavior and memory. The key insight was that simple elements mimicking these neurons could perform complex logical operations like AND or NOT. This was foundational for AI. This notion that complex intelligence could emerge from the collective action of many simple, interconnected units.
Wow. Okay, and this wasn't just theory, they actually described how it could work.
Exactly. Their work wasn't purely theoretical. Just 4 years later, in 1947, they published How We Know Universals. In it, they described network architectures capable of recognizing spatial patterns that remain invariant under geometric transformations.
Okay, invariant under, what does that mean practically?
Imagine being able to recognize a square, for instance, regardless of whether it's big or small, sitting straight up or tilted, or even if it's shifted to a different part of your visual field. This was a very early, yet incredibly profound form of pattern recognition. It unequivocally established the concept that simple interconnected units could form sophisticated computational systems that could actually learn to generalize from their environment, a true aha moment for the field.
Right. So the idea of interconnected systems that learn and adapt wasn't just in this realm of theoretical nerve cells and logic. Around the same time, you mentioned another visionary, Norbert Wiener, developing this field of cybernetics, and that was deeply rooted in the concept of feedback. Sounds like another absolutely crucial piece of the puzzle.
It really was. If we connect this to the bigger picture, Wiener's work on cybernetics provided a crucial overarching framework. It helped understand how systems, both biological and mechanical, could achieve goals through self-regulation. The core idea is simple but profound. Information about the output of a system is fed back into the system, influencing its future actions. This feedback loop is absolutely fundamental to any form of learning, especially reinforcement learning. It's how a system knows if it's on the right track or needs to, correct course.
Makes sense. You need to know if what you did worked or not.
Exactly. And Wiener famously highlighted a critical balance. He said, excessive feedback is likely to be as serious a handicap to organized activity as a defective feedback.
Huh. So too much correction can be as bad as too little.
Precisely. Think about that for a moment. Too much or too little can both be equally problematic. He brought this concept to life with a really vivid illustration. He recounted a conversation with a Dr. Rosenbluth about something called purpose tremor. This is a pathological condition where a patient trying a voluntary act, say trying to touch their nose, overshoots the mark. And then they go into this uncontrollable oscillation, repeatedly missing and overcorrecting, often associated with cerebellum injury.
Wow.
It serves as this striking physiological analogy for uncontrolled feedback in a learning system. If the corrective signal is too strong or too frequent or maybe arrives too late, the system can become unstable, just can't settle on the right action.
Like constantly oversteering a car.
Exactly like that. And Wiener also theorized about how information could be stored in the brain. He suggested it could happen by changes in the thresholds of neurons or by changes in the permeability of each synapse to messages. This concept of synaptic plasticity, the strengthening or weakening of connections between neurons, is absolutely fundamental to how modern neural networks learn through reinforcement. It's how the system dynamically adapts its internal structure based on feedback, whether that feedback is a clear reward or an undesirable punishment. It showed learning wasn't just about processing information, but about changing the very architecture of the processing unit itself.
Okay, so with these foundational ideas from McCulloch, Pitts, and Wiener, the stage was set. Researchers started moving beyond pure theory, thinking about building actual learning machines. And one of the most famous early attempts, the one that really captured the imagination, was the perceptron, a kind of single-layer neural network. It felt like a tangible, exciting step towards AI that could genuinely learn.
Yes, but this raises an important question, doesn't it? About that early optimism and its eventual, maybe unavoidable, collision with the practical realities of computation. The perceptron, developed by Frank Rosenblatt in the late 1950s, was a powerful symbol of early AI ambition. It had this remarkable convergence theorem, which proved that if two sets of figures are linearly separable, then the convergence theorem procedure can find a separating predicate.
Okay, linearly separable, in plain English.
Right. Imagine you have data points on a graph, and you want to separate them into two categories, say pictures of cats versus dogs. If you could draw a single straight line, or maybe a flat plane in higher dimensions, to perfectly separate those two categories, the perceptron was guaranteed to learn how to do it. It would, through this process of error correction, eventually find that separating line. This was a huge demonstration. Simple linear threshold decision elements, much like McCulloch and Pitts envisioned, could learn to classify patterns based on input. Its learning mechanism was a direct form of reinforcement. Any errors, misclassifications led to automatic adjustments in its internal weights, incrementally pushing it closer to a correct classification.
So it could reliably learn simple pattern recognition tasks, essentially by finding that dividing line. That sounds pretty powerful for the era. What happened then? Why didn't it just take over?
It was powerful for its niche, absolutely. But this early promise was met with a devastating and, frankly, historically significant critique. Marvin Minsky and Seymour Papert's seminal book, Perceptrons, published in 1969, it rigorously exposed the inherent limitations of these single-layer networks. Their analysis, particularly highlighting the perceptron's inability to solve non-linearly separable problems, was a severe blow.
Non-linearly separable, meaning you couldn't draw that single straight line.
Exactly. The most famous example they used was the parity problem. Imagine you have two inputs, each being either 0 or 1. The parity problem asks you to output 1 if the inputs are different, 0, 1, or 1, 0 if they're the same, 0, 0, 1, 0, 1. If you try to plot those 4 points on a graph, you'll quickly realize you cannot draw a single straight line to separate the 1 outputs from the 0 outputs. You just can't.
Ah, I see.
The problem required complex, nonlinear distinctions that single-layer perceptrons simply couldn't make.
So it was like hitting a brick wall.
Yeah.
The perceptron, despite its initial success, was fundamentally limited in the kinds of patterns it could learn.
Exactly. This exposed their profound struggles with complexity. It was a critical insight. It revealed that while individual neuron-like units could do simple logic, a single layer of them couldn't achieve true nonlinear intelligence. And this book, coming from 2 giants of AI, Minsky and Papert, well, it contributed significantly to a downturn in funding and interest in neural networks. For nearly 2 decades, really, a period often called the AI winter for these connectionist approaches. Minsky also later contrasted this simple architecture with the brain, suggesting the brain isn't a single, uniform, highly interconnected assembly of units, but rather a society of mind with various specialized networks and control systems that interact in structured ways.
Interesting.
And this insight was crucial. It highlighted the need for controlled, maybe hierarchical interactions to avoid uncontrollable interactions and fragile systems. It implied that simple, undifferentiated reinforcement wouldn't scale for truly robust or intelligent systems. Learning, they argued, needed more structure than just one layer of connections.
First steps in trial and error. The birth of reinforcement learning.
Okay, so even amidst these early challenges for perceptrons and what felt like an AI winter for neural networks, the core idea of learning from experience, of using reinforcement, was just too powerful to disappear.
Right.
It was clear that explicit programming alone wasn't going to cut it for truly intelligent systems. How then do we define this early concept of reinforcement learning? And what did it actually look like in practice, especially in an era with, severely limited computational power and much simpler models?
Right. We define reinforcement learning quite broadly, actually, as any effective way of solving reinforcement learning problems. And what are those problems? Well, they are very closely related to optimal control problems, especially those mathematically formulated as Markov Decision Processes, or MDP.
Okay, MDPs. That sounds a bit technical.
It does, but let's break it down. Essentially, reinforcement learning is about an agent, our AI learning to make a sequence of decisions. It does this by performing actions in an environment to maximize some notion of cumulative reward over time. Think of it less like programming every single step and more like programming a system to learn how to achieve goals through, well, guided trial and error. Optimal control methods, things like dynamic programming, are actually considered part of RL. These methods are inherently incremental and iterative.
Meaning they don't just jump to the answer?
Exactly. They don't find the perfect answer all at once. Instead, they gradually reach the correct solution through successive approximations, refining their understanding step by step, much like true learning methods. This highlights the gradual trial and error nature of the learning process itself.
So an agent takes an action, sees what happens, gets some kind of reward or penalty, and then adjusts its strategy to get more rewards in the future. And what about this Markov Decision Process thing?
Precisely. The MDP is simply a mathematical framework for modeling this decision-making puzzle. Imagine an agent, like a robot, existing in a world made up of different states, like being in a particular room or holding a specific object. The robot can take actions, move left, pick up, open a door, and when it takes an action, the world might change to a new state, and importantly, it might receive a reward or a punishment. Crucially, in a Markov system, the next state only depends on the current state and the action taken, not the entire history of how it got there. It simplifies the problem considerably.
Okay, got it. Doesn't need to remember everything that ever happened.
Right. And within this framework, a policy is a key concept. Its mind is the action recommended by the policy for state S. So the policy is essentially the agent's strategy, its rule book that says, if you're in this state, take that action. An optimal policy is, naturally, the one that yields the highest expected utility or cumulative reward over the long run. The ultimate goal in reinforcement learning is to discover or learn this optimal policy. And crucially, this learning involves dealing with the stochastic nature of the environment.
Stochastic meaning?
Random.
Unpredictable.
Exactly. The world isn't perfectly predictable. Each time a given policy is executed, starting from the initial state, the stochastic nature of the environment may lead to a different environment history. So the agent has to learn to cope with uncertainty and variability, just like we do in the real world when we learn a new skill. You don't always get the exact same outcome, even if you try the exact same thing.
Right. And what better way to test a machine's ability to learn through this kind of trial and error than with games? Games offer clear goals, defined rules, often a definitive win or lose state perfect for these reinforcement signals. Seems like a natural proving ground, a sandbox for intelligence.
That's absolutely right. Games were critical. If we connect this to the bigger picture, even Alan Turing, one of the true intellectual pioneers of computer science, along with his friend David Champernowne, developed an early chess-playing program called TurboChamp back in 1948. While it was rudimentary, often executed by hand, this was a very early visionary foray into machines tackling strategic games. However, the first significant application of reinforcement learning in a practical, demonstrable sense was probably Arthur Samuel's checkers program. He developed it starting in 1959 and refined it further in 1967. This program was revolutionary, not just for playing checkers, but because it fundamentally shifted away from relying on explicitly coded strategies for every possible move. Instead, it learned by playing itself.
Learning by playing itself.
Yeah.
That's incredible for the late 50s. How did that even work without being explicitly told what moves to make?
It was ingenious. Samuel's program used a weighted linear function to evaluate positions on the checkers board. Think of it like a scoring system. This function had up to 16 terms, representing different aspects of the board state, things like the number of pieces each player had, how many kings, how many pieces were blocked, and so on. Okay, so different features of the game. Right. Each feature had weight associated with it, indicating its importance. The program would generate possible moves, evaluate the resulting board positions using this function, and choose the move that led to the highest scoring position. The genius part was that these weights were not fixed. They were updated to improve the program's play. Now, here's where it gets really interesting and directly addresses our focus on early struggles and clever solutions. Samuel's program initially did not use any observed rewards. That is, the values of terminal states reached in self-play winning or losing the game were ignored.
Wait, so it learned by playing itself, but it wasn't even told if it won or lost a game. How could it possibly learn to play well then? It sounds like it theoretically learned to lose.
Exactly. You've hit on the critical point, a profound struggle with complexity that Samuel encountered. Without an explicit reward signal for winning or punishment for losing, it was theoretically possible for the program to converge on a strategy designed to lose rather than to win, or just, wander aimlessly in the space of strategies. It was essentially optimizing for some internal evaluation score, but not necessarily a winning one from a human perspective.
So what did he do? How did he fix that?
Samuel's ingenious solution to this fundamental problem was a stroke of brilliance born of necessity. He introduced a fixed bias, a simple rule. He managed to avoid this fate by insisting that the weight for material advantage should always be positive.
So he hard-coded that having more pieces is always good.
Essentially, yes. This seemingly simple, almost manual rule effectively baked in a basic overarching reinforcement signal. It told the program, more pieces are generally better. And this was sufficient to direct the program into areas of weight space corresponding to good checkers play. It demonstrated how even a subtle initial reinforcement signal, a guiding hand from the designer, could steer the learning process in a complex task towards a desired outcome, even when full environmental rewards were absent or not explicitly used.
Wow.
It was a foundational insight. Reinforcement doesn't always have to be explicit, like a win-loss signal. It can be subtly engineered into the system's objective function. And Samuel's program didn't just play, it learned so well it could defeat its own creator and even skilled human players. A landmark in AI history.
Learning mechanisms in early neural models.
Okay, so if Samuel's program relied on adjusting weights, and the perceptron also adjusted weights based on error, how did these early neural networks actually learn? How did they adjust their internal workings based on this trial and error? What were the precise mathematical underpinnings of this reinforcement process? It wasn't just about the broad idea of rewards and punishments. There had to be concrete ways for the network to adapt itself.
Right. And what's fascinating here is the delta rule. This was a truly foundational learning algorithm for adjusting those weights, the strengths of connections, in a neural network. It's essentially an error correction learning rule, a direct mathematical implementation of that iterative trial and error process we've been discussing. The delta rule works by calculating the difference between the network's actual output and what the desired target output should have been. This difference, this discrepancy, is what we call the error signal. Think of this error signal as a very direct form of punishment for mistakes, and conversely, a kind of implicit reward for being correct. If the network's output is too low compared to the target, the weights contributing to that output are adjusted upwards. If it's too high, they're adjusted downwards, incrementally, with each learning step.
So it's constantly comparing what it did to what it should have done and just nudging itself closer to correctness each time.
Exactly that. It's like a sculptor gently chipping away at a block of marble. Each chip isn't a massive change, but it's guided by where the final desired shape isn't yet. The mathematical expression you often see is something like Wn-1 ease NINTC.
Whoa, okay, math.
Yeah, let's break that down conceptually. Wn is just the current set of connection weights. Wn1 was the set before this adjustment. The adjustment is determined by a few key things. Eta is the learning rate, a small number controlling how big each adjustment step is. Too large, it might overshoot. Too small, it learns incredibly slowly. Eta in is that crucial error signal we just discussed, the difference between target and actual output. INT represents the specific input pattern that caused this error, and C is a matrix holding info about correlations among input patterns, though let's maybe not dive too deep into that part.
Okay.
So in essence, the rule says, adjust your internal connections, W, in proportion to the error you just made, considering the input I that led to it, and do it gradually. This iterative adjustment, guided by that clear error signal, enabled networks to gradually improve performance by systematically reducing the gap between what they did and what they should have done. A powerful practical mechanism for learning.
That's a very clear way to visualize it, thanks. But beyond this direct error correction, other researchers were exploring completely different avenues, weren't they? Some looked to statistical mechanics, physics dealing with probability in large systems, for ways to allow neural networks to learn more complex internal representations and understand underlying probability distributions. This sounds like a much more abstract approach than just fixing an error signal.
It was, and this raises an important question about exploring diverse inspirations for AI, right? Drawing from fields far beyond traditional computer science. Boltzmann machines, which emerged in the 1980s, were a significant departure. They offered a general connectionist approach to learning arbitrary probability distributions over binary vectors. Instead of needing explicit input-output pairs to correct, these networks aimed to learn the hidden statistical regularities within the data itself.
So finding patterns without being told exactly what pattern to find.
Sort of, yes. They were a significant development in neural models, seeking to learn complex patterns without relying solely on direct, explicit supervision in the same way the Delta Rule did. Developed by influential figures like Jeffrey Hinton, Terry Signowski, Scott Fahlman, names that are still huge today. Boltzmann machines represented a bridge between neural network concepts and statistical physics, particularly the idea of energy functions.
Energy functions, like in thermodynamics, how does that relate to a neural network learning something?
It's an elegant analogy, actually.
Yeah.
In these models, each possible state of the network, each configuration of its binary units being on or off, has an associated energy. The network tries to settle into low-energy states, which correspond to the patterns it has learned from the data.
Like a ball rolling down a hill seeking the lowest point.
Exactly like that. The network tries to find the lowest energy configuration that best represents the patterns it's seen in its training data. Learning in Boltzmann machines involved adjusting the connection weights to shape this energy landscape, essentially, to minimize the overall energy function for configurations that match the data. This effectively moved the network towards configurations that represented learned patterns or structures. The process involved a form of stochastic search. It incorporated randomness, like how physical systems can jump between energy states at a given temperature.
Okay, why the randomness?
That allowed them to escape local minima configurations that are low energy but not the lowest, and potentially find deeper, more meaningful patterns. It was an ambitious attempt to create networks that could discover hidden structures and probabilities in a distributed, self-organizing way, moving beyond simple classification towards understanding the underlying generative process of the data itself.
Right. So as networks grew more sophisticated and researchers grasped these varied learning mechanisms, the focus naturally shifted. It moved towards how their internal structure, their architecture, contributed to their overall learning capabilities. The idea of parallel distributed processing, or PDP models, became incredibly influential then, suggesting that how the units are arranged and interact is just as important as the learning rules themselves.
Indeed. It implied intelligence wasn't just about a single calculation, but a complex, coordinated dance of many calculations happening simultaneously. The parallel distributed processing models, brought to prominence by the PDP group, including luminaries like James McClelland and David Rumelhart in the mid-1980s, emphasized that complex cognitive phenomena like memory, language, perception could be described by the collective units and activations of units operating at a micro level. This was a radical shift from earlier symbolic AI, which tried to represent knowledge as explicit rules and concepts, like in a database. In PDP, knowledge wasn't stored in single concepts residing in a specific unit, like a memory slot. Instead, it was encoded as distributed patterns of activity spread across many, many units.
So a single memory or concept wouldn't be in one specific neuron, but rather in the way many neurons light up together in a particular pattern.
Exactly. Think of a symphony orchestra. No single instrument creates the entire melody. It's the pattern of all instruments playing together. Similarly, in PDP models, the effect of a pattern of activity on other representations is the combined result of the individual effects of the active units in the pattern. This means, and this is crucial, that similar patterns tend to have similar effects, which is a fundamental and incredibly powerful property for generalization.
Generalization, meaning it can handle things it hasn't seen before.
Right. If the network learns to recognize one type of cat, it will naturally have similar responses to a slightly different cat it hasn't seen before, because the underlying pattern of activity across the units is similar. These models often featured complex internal structures far beyond simple feed-forward layers. We're talking about pools of mutually inhibitory units, where units would actively suppress each other's activity, maybe to sharpen distinctions, and things like symmetric connections, where if a hidden unit was turned on by an input unit, it would in turn try to turn on that same input unit, creating a kind of resonance or associative memory.
Wow, sounds complicated.
It was. This intricate interplay of activations and inhibitions allowed for sophisticated pattern recognition and learning. Even if individual units didn't have explicit direct rewards or punishments in the most immediate sense, their contribution to an overall error signal or objective function meant the entire distributed system was learning. It was refining its internal representations through a form of collective reinforcement, making small, distributed adjustments to these complex interactions to improve overall performance. A holistic, system-wide approach to learning from feedback.
The path to modern breakthroughs, lessons learned, and seeds planted.
Okay, looking back, it's clear these early models, from the conceptually powerful but limited perceptrons to Samuel's pioneering checkers player, they faced significant challenges, exposed fundamental limitations. But these struggles were far from failures. They were crucial learning moments, weren't they? They led to deeper insights and fundamental questions that continue to shape AI research today, really laying the groundwork for everything that followed.
Absolutely. What's truly fascinating here is how these early difficulties weren't dead ends, but rather catalysts for deeper theoretical development. The difficulties encountered by Samuel's checkers program, for instance, in its initial lack of observed rewards, that really underscored the critical need for robust feedback mechanisms. That absence meant the system could theoretically optimize for unintended outcomes, as we discussed learning to lose. This foundational problem of how an agent should learn about its environment led to a key debate in AI that persists even now, although in more sophisticated forms. Is it better to learn a model and a utility function, or to learn an action utility function with no model?
That's an interesting distinction. Learning a model sounds like trying to understand the whole world, build a map of it, while learning an action utility function seems more focused on just knowing what to do next without the map. Can you break that down for us?
You've got the gist of it, yeah. It refers to the contrast between two major families of reinforcement learning methods. On one side, you have approaches like adaptive dynamic programming, or ADP. These methods try to build an explicit model of the environment. They learn how actions affect states, what the rewards are for transitioning between states. It's like building a miniature simulation of the world inside the AI's mind. With this model, the AI can then plan ahead, simulating different actions to find the best utility, the best outcome.
Okay, so model-based. It learns the rules of the game.
Right. Then on the other side, you have model-free methods like Q-learning or SARSA. These learn an action utility function, often called a Q function. This function directly estimates the value, the expected future reward, of taking a specific action in a given state without explicitly building a full environmental model. It's more like learning from raw experience, directly mapping situations to the best action, rather than understanding the underlying physics or rules of the entire world.
So one builds a map of the world, and the other just learns the best route without needing to see the whole map.
Precisely. Q-learning, for example, tries to learn the maximum expected future rewards for taking a particular action in a given state. It's quite optimistic. SARSA, on the other hand, is a bit more conservative. It evaluates the reward based on the next action that the current policy would actually take. Now, while model-free methods like Q-learning and SORSA can sometimes be slower to learn than model-based ones like ADP in certain controlled scenarios, they offer greater flexibility. They can often learn optimal policies even when the environment is complex, unpredictable, or even adversarial, precisely because they don't rely on having a perfect internal model, which can be hard or impossible to build.
Makes sense. Less brittle, maybe.
Could be, yeah. This highlights the deep trade-offs that emerge from early reinforcement learning research. The choice between building a comprehensive internal representation of the world or learning directly how to act effectively within it. It's a tension that still exists. And beyond these technical questions, these early neural networks also raise profound philosophical implications. The idea of jumbles of neurons passing around jumbles of numbers, as some critics put it, sparked discussions about intelligibility. It reminds us that even if these systems learn and perform complex tasks, understanding how and why they make their decisions is a fundamental challenge, one that continues from those early neural nets right through to the complex black boxes of modern AI.
Okay, so all these early attempts, the theoretical groundwork, the trial and error in games, the evolution of network architectures and learning algorithms, they all planted seeds. And these seeds, after decades of patient development and crucially massive computational advancements, eventually blossomed into truly astonishing achievements. Perhaps most famously, this came to a head in the ancient game of Go, a game far, far more complex than checkers, which had long been considered the ultimate grand challenge for artificial intelligence.
Absolutely. If we connect this to the bigger picture, the principles of combining neural networks with sophisticated reinforcement learning algorithms, principles which began with that rudimentary trial and error in simple games, they culminated decades later in systems like DeepMind's AlphaGo. Its victory over Go legend Lee Sedol in 2016 was, well, it's a monumental moment in AI history, a stark demonstration of how far these foundational ideas had come. It wasn't just a win, it felt like a paradigm shift. AlphaGo famously made that highly creative move on line 5 during the 37th move of the second game against Sedol, move 37. This move utterly defied millennia of human wisdom, centuries of accumulated Go strategy. Initially, human commentators, top Go players, even Sedol himself, were completely puzzled. They thought it was a mistake, a blunder.
So human experts literally couldn't understand what the AI was doing.
That's incredible. It really was. It took nearly about 50 moves later for the true genius, the deep strategic implication of that unconventional move to become clear. It proved crucial to its defeat of the world champion, revealing a deep strategic understanding that humans had simply never conceived of. This was a profound demonstration. Reinforcement learning, when scaled up and combined with powerful neural architectures, specifically deep neural networks, could not only master incredibly complex tasks, but could also exhibit a form of intuition and logic, leading to genuinely creative actions that went far beyond explicitly programmed rules or even the vast corpus of human game records it learned from initially. It wasn't just following a massive search tree or mimicking human play anymore. It was discovering novel strategies through deep learning and extensive self-play, driven by incredibly refined reinforcement signals. This was a machine learning to be genuinely innovative.
And these breakthroughs weren't confined to mastering ancient board games, as astonishing as that was. The same underlying principles, the lessons learned from those early struggles and successes, have powered advances in fields like robotics, right? And even how our large language models learn to communicate in ways that feel incredibly natural and helpful. We're seeing the direct lineage of Samuel's checkers player in the AI systems we use every day.
Absolutely. And this raises an important point about the widespread transformative impact of these evolving concepts across diverse domains. The success of systems like AlphaGo showed how those early ideas of rewards for correct actions have evolved and scaled to, frankly, unimaginable levels.
Yeah.
Today, we see reinforcement learning fine-tuning, or RLHF, being used extensively to train powerful language models like ChatGPT. It's a direct, though much more sophisticated descendant of that early trial and error process.
Okay, RLHF. How does that work for something like a language model? It's not playing a game with clear wins and losses, is it?
No, it's a clever adaptation. RLHF involves creating a separate reward model. This reward model learns to judge the quality of responses generated by the main language model. And how does it learn to judge? Often it's trained on human feedback to rate pairs of responses, saying which one is better, more helpful, safer, or more aligned with the user's instructions.
Ah, so humans provide the reward signal indirectly.
Exactly. The reward is no longer just winning a game, but this nuanced judgment learned from human preferences. Once this reward model is effective, the original language model is then fine-tuned using reinforcement learning techniques, often sophisticated algorithms like proximal policy optimization or PPO. The goal for the language model becomes maximizing the score given by the reward model, so it learns to generate responses that humans are likely to prefer. This is a direct, albeit highly advanced, descendant of those early trial and error methods, but with human feedback subtly guiding the rewards in a much more nuanced and complex way than just positive material advantage.
Okay, that makes sense. And what about robotics? You mentioned that too. How does this connect there?
Well, the foundational link between optimal control problems and reinforcement learning, established way back in those early definitions, absolutely underpins how robots learn to perform tasks in the messy, dynamic physical world. Think of a robotic arm learning to pick up an irregularly shaped object it's never seen before. Instead of being explicitly programmed with every possible angle, force, and gripping motion, which would be impossible, it learns by trial and error. It attempts to grasp the object, gets feedback. Did it drop it? Was the grip too weak, too strong? Did it knock something over? And then it adjusts its motor commands, its grip strength, its approach trajectory for the next try.
So it's literally learning through doing, getting physical rewards or punishments.
Precisely. This is where the optimal control roots of RL become really visible in the physical world. The robot is learning the best sequence of movements to achieve a task, even with real-world variability in physics, by optimizing for desired outcomes or rewards. It is literally teaching itself how to interact effectively with its environment. And looking even further ahead, the ongoing work on alignment methods for superintelligence and the dedicated superalignment teams at leading AI labs. This further underscores the continuing relevance of ensuring these increasingly capable AI systems learn to pursue human beneficial goals or rewards.
Right.
It's about making sure the AI's complex learning objectives align with our values right from the foundational reward structure as these systems become more autonomous and powerful. It all comes back to getting that reinforcement signal right. Outro.
What an incredible journey we've taken today. Seriously. From the simple logical networks inspired by biology, through the profound challenges of teaching machines to play checkers with pretty rudimentary feedback, all the way to systems that defeat world champions in games of unparalleled complexity and help shape the very language models we interact with every single day. It truly shows how far a simple yet powerful idea, this concept of learning from experience, from rewards and punishments, can take us.
Indeed. And the early struggles with complexity, like the perceptron's limitations or Samuel's ingenious workaround with that fixed material advantage weight and the iterative adjustments of the delta rule, these weren't just isolated stepping stones. They were fundamental explorations of how intelligence itself might emerge from continuous interaction and feedback. They forced researchers to confront deep questions about how best to represent an agent's knowledge and goals, whether through an explicit internal model of the environment or by directly learning an action utility function that guides behavior. This historical trajectory reveals this continuous thread of inquiry into how machines can adapt and improve, evolving from simple nudges to sophisticated, self-organizing systems.
And what does this all mean for you, listening in, as a learner and an observer of this rapidly evolving field? Well, it means understanding that today's smart AI isn't some kind of magic black box that just appeared. It's built on decades of foundational research into how to get machines to learn from what happens next, refining their actions through a continuous, often incremental, loop of trial, error, and reinforcement signals. It's really a testament to the power of breaking down incredibly complex problems into manageable, iterative learning steps, a process that in many ways mirrors our own journey of discovery and skill acquisition.
Right. And this raises a final important question, maybe, about the future of AI motivation. One where we can draw parallels to our own biology. Consider how the human pleasure systems help us learn, and therefore to behave ourselves, by forcing checks and balances on us. Just like our own biological systems tend to satiate if we do the exact same rewarding thing over and over again, requiring novelty and varied experiences to remain engaged.
Good point. We get bored.
Exactly. Future intelligence systems will likely need more sophisticated, perhaps even intrinsic motivational structures. Relying solely on external rewards, especially simple ones, could lead them to getting trapped into endlessly repeating the same activity, or finding clever but undesirable loopholes to maximize reward without achieving the intended goal, the so-called reward hacking problem. This ongoing challenge, connecting the biological underpinnings of learning and motivation with artificial systems, suggests that the deep dive into reinforcement in neural models is far from over. It's a journey that began with abstract neurons and checkers games, and it continues to push the very boundaries of what it means for any entity, biological or artificial, to learn, adapt, and be truly intelligent.